Oh, things are getting serious. Find the derivative of f of x equals 2x squared plus 3x using the definition of the derivative. Well, if I give you f of x, then we would call the derivative f prime of x. But what is the definition of the derivative? Well, it's the same thing as instantaneous rate of change, of course. The limit as h approaches 0 of f of x plus h, like that, minus f of x over h. So what we need to do is we need to find out what f of x plus h is, right? We have f of x, plug stuff in, hope things disappear, and wish for the best. F of x plus h means I'm going to take f of x and replace every x with x plus h. So u become 2 times parentheses x plus h, close it, square it, plus 3 times x plus h. Okay? Now, this is a perfect square trinomial, so the 2 remains out there for now. X plus h squared becomes x squared plus 2xh plus h squared, right? Distribute. So you become 3x plus 3h. And then when I distribute the 2 to all of that, I get 2x squared plus 4xh plus 2h squared, and then 3x and 3h come along for the ride. We already know what f of x is, so I'm not going to bother writing it down. So what I'm going to do is I'm going to rewrite this guy out, okay? The limit as h approaches 0 of f of x plus h, so I'm going to write that in blue. That became 2x squared plus 4xh plus 2h squared plus 3x plus 3h minus f of x, which I underlined in purple, so minus 2x squared plus 3x, close that, all over h, like that. Okay, let's distribute that guy. So limit as h approaches 0, nothing in blue changes, nothing at all. I'm just rewriting it out like that, like that. Distribute the negative, minus 2x squared minus 3x. And when you have polynomials like we have here, you're hoping for stuff to disappear, which is going to happen now. 2x squared, adios. 3x, adios to you. And you're left with the limit as h approaches 0 of 4xh plus 2h squared plus 3h over h. Now notice all of these guys have h's, which means I can factor out an h. When you're dealing with polynomials like what we have up here, expect that to happen every single time when we have polynomials. Not every single problem, but every single time when I have polynomials. If I have an h, bring it out. 4x plus 2h plus 3, close it, all over h. See, the initial problem, by the way, is like when I got to this point after I plugged stuff in, if you're like, why don't we just plug in 0 for h? Well, you get 0 on the bottom. That's no good. But now h crosses out. And we are left with the limit as h approaches infinity of 4x plus 2h plus 3. So all I have to do here is replace h with 0, and I get 4x plus nothing plus 3. So after all of that, f prime of x equals 4x plus 3, which is b, baby. Wasn't that fun? Find the derivative of f of x equals 1 over x using the definition of the derivative. Well, if I have f of x, that means I'm trying to find f prime of x. Now, what's the definition of the derivative? Well, that's the limit as h approaches 0 of f of x plus h minus f of x all over h. So what I have to do is I know what f of x is. Okay, there you are, your f of x. I need to find out what f of x plus h is. And really all I have to do here is substitute x with x plus h, and I get 1 over x plus h. So that's not so bad. So let's continue the problem and see what happens. And I know I'm going to have radicals or rationals or whatever they're called, and no one likes those, but nah, I'll be all right. I'll just give myself plenty of space. F of x plus h was 1 over x plus h minus f of x was 1 over x, giving myself plenty of space, all over h. Here's the issue. Can't plug in 0 for h because I get 0 on the bottom. That's no good. So what I'm going to want to do first is I'm going to want to combine these fractions up here in the numerator. That's why I left all that space there. And the way you're going to do that is you're going to multiply this guy by x over x and this guy by x plus h over x plus h. And that way I'll have on the top x times x plus h, like so. You become x, you get distributed, but it's a minus sign. Oh, be careful. So it's minus x minus h, that was a close one, all over h. So I'm still dealing with the limit as h approaches 0 of u2 cancel out, negative h over, let's distribute that out, x squared plus xh all over h. Again, h on the bottom is an issue. So why don't I multiply the top and the bottom by its reciprocal, 1 over h, 1 over h. That way the h and the 1 over h on the bottom cancel out. And lo and behold, looky what happens. That h and that h also cancel out. So that leaves me with the limit as h approaches 0. Negative times 1 is negative 1, all over x squared plus xh. Now I'm okay to plug in 0. And if I plug in 0, I end up with negative 1 over x squared plus x times 0, which makes u go away. So negative 1 over x squared is going to be my derivative. So let me write it out. F prime of x equals, let me pull that 1 completely out, negative 1 over x squared, which in this case is going to be a. Crazy fun. Let f prime equal the limit as h approaches 0 of x plus h squared minus x squared over h. For what value of x does f of x equal 4? Well, I give you the derivative. And by definition, the derivative is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. This problem wants me to find out when f of x is 4. But I'm not given f of x. I'm given f prime of x. Oh, but wait a minute. If f prime of x is f of x plus h minus f of x, that means this guy right here, f of x, is the same as x squared. So the original f of x must have been x squared in order to get to this point that we have here, which also makes sense because f of x plus h would just be x plus h squared. So, all right, that makes sense. Well, f of x is 4. So if f of x is 4, I could just replace f of x with 4 and say 4 equals x squared. In order to get x all by itself, I positive negative square root this guy. That crosses out. And x is going to equal plus or minus the square root of 4, which is 2. Okay. Now, in this case, it only wants me to probably do one of them. It's only giving me the one option, which is 2. But technically, there is 2 answers here. So, I mean, that's kind of exciting, I guess. But, yeah, that's how you do it. Kind of a weird problem. Working backwards on that one. For function f, we are given f of 5 equals negative 8 and f prime of 5 equals negative 6. Identify the y-intercept of the line tangent to f at x equals 5. So I'm just going to draw some like random graph, all right? Looking at what we have here, the derivative gives you slope at a specific point. It's a slope of the tangent line at a point. So if I were to call you 5, all right, if this was 5, the slope at 5 would be negative 6. Now, granted, my picture is not super accurate, but you get the right idea. Now, what we also know is that at this moment right here, okay, the slope is negative 6, but the point 5 also has a y-coordinate of negative 8. So we have a slope of -6, and also this right here is telling us that we have a point of 5, -8. My job is to identify the y-intercept of the line tangent to that. So what I'm going to do is I'm going to build a slope-intercept form equation for the slope of the tangent line, and from there I'll be able to identify the y-intercept. So if I have y equals mx plus b, that's slope-intercept form. I already know that the slope of the tangent line is -6. So what I have so far is y equals -6x plus b. I also know that I'm given the point 5, -8. So if I call you x and I call you y, I can substitute for y, -8, and I can substitute for x, 5, and do a little bit of math. So plus b is going to give me my y-intercept. So this is -8 equals -30 plus b, add 30, and b is going to be the Taylor Swift special, 22. So just for funsies, the graph, or the equation rather, that I would get would be y equals -6x plus 22. In my case, the y-intercept of the line tangent to f at x equals 5, the y-intercept is going to be that number 22. Okay? That's how you do it.